We've discussed London dispersion forces, which are typically the weakest of the three types of intermolecular forces. Yet in that example in our previous video, we saw that sometimes isn't the case when the size of the electron cloud is really, really big. We then talked about dipole-dipole forces that occur between polar molecules. So London dispersion forces, if it's a non-polar compound, it only has London dispersion forces. If it's a polar compound, it has dipole-dipole forces and London dispersion forces. So those are our first two types of intermolecular forces. Our third and final type of intermolecular force is what's called hydrogen bonding. One of the ways that I discuss hydrogen bonding is in between hydrogen and the word bonding is I put the word not. Okay, don't ever use that on a test, but and again, these are the chemistry people that come with these things. It's not a bond, okay? It's called hydrogen bonding, hydrogen, not bonding, okay? But it's not a bond. It is, again, this is not a bond, okay? It is a type of intermolecular force. It's an attraction between one molecule and another, okay? And it's much, much weaker than a bond, okay? All intermolecular forces are always weaker than a bond. Even though, again, we do call it hydrogen bonding, again, not a bond, an intermolecular force, okay? Now, how is hydrogen bonding different from dipole-dipole forces or London dispersion forces? It's very, very simple, okay? Obviously, it has to have a hydrogen in it. If a hydrogen atom is bonded, so again, a real bond, it has to be bonded to an N, an O, or an F. And nitrogen, oxygen, and fluorine are really, really small atoms, and they're also really, really electronegative. We'll talk about that more in just a second, okay? So if the hydrogen is bonded to, and again, not a fake bond, a real bond, if it's bonded to an N, an O, or an F, but is also attracted to an N, an O, or an F in a different molecule, and no, they don't have to be the same, that's a hydrogen bond. Okay, an intermolecular hydrogen bond. So hydrogen can be bonded to nitrogen, such as this, but then attracted to a fluorine in a different molecule. So right there, that right there would be the hydrogen bond. The hydrogen's bonded to an N, an O, or an F, and then it's attracted to an N, an O, or an F in another molecule. Again, this right here, not the hydrogen bond. That's a covalent bond between nitrogen and hydrogen. Okay, this right here, this attraction right here that occurs between the hydrogen in one molecule and, again, a nitrogen, oxygen, or fluorine in another molecule is that intermolecular hydrogen bond. Okay? Now, the reason that these are absolutely, of the three types, hydrogen bonding is absolutely the strongest type of intermolecular force. If it has hydrogen bonding, it will have the strongest intermolecular forces. Okay? Part of the reason why is because it talks about here, about hydrogen, that one electron that it has is on one side. Like here in this bond, the hydrogen electron is over here, and that leaves the other side completely exposed. This side over here is completely exposed. So any negative group, so fluorine, for example, that can get close produces a really, really strong electrostatic attraction, okay? And it especially happens when the other element is really, really electronegative. So that's why, again, that's why it has to be N or O or F in order for it to be considered a hydrogen bond, okay? So, in a bond, in a molecule such as HF, okay, if they say list all of the different intermolecular forces that occur between molecules of HF, the answer is London dispersion forces, because every molecule has London dispersion forces. Is HF polar? Absolutely it is. So you'd say dipole-dipole. And HF does also exhibit intermolecular hydrogen bonding, so you got to list all three of them. So when they say list all types of intermolecular forces and it has hydrogen bonding, then you have to list all three of them. Now, if they say what accounts for the difference in the boiling point of this versus the boiling point of that, then typically it's going to be just the strongest of the three. It's going to be the hydrogen bonding case. Okay? So let's look at an example here. Here's an example where they give you a whole ton of information. Who really cares about any of this? Really, all that we care about is basically which of these actually shows, denoted by dashed lines, which of these shows hydrogen bonding correctly. Oh, so hydrogen is forming, again, an intermolecular attraction with oxygen. And here it is with nitrogen. Okay, oh, is that hydrogen bonding? No, it's not. And the reason it's not is because, remember, hydrogen has to be attracted to an N, an O, or an F, which it is, but it must also be bonded to an N, an O, or an F. Okay, and here you can see the hydrogen is bonded to a carbon, the hydrogen is bonded to a carbon. That's a no. Okay, answer B, you've got N attracted to O. There's no hydrogen there at all, so right away, that's a no. It has to be a hydrogen that's attracted to an N, an O, or an F. Okay, in C, a hydrogen, first of all, is bonded to carbon and then attracted to just another hydrogen. Again, not even close. Here, at least the hydrogen's bonded to a nitrogen, but then again, attracted to a hydrogen, not even close. Okay, and then in answer D, you can see everything is met. Okay, the hydrogen, both hydrogens are bonded to an N, an O, or an F, and then each of those hydrogens is also attracted to an N, an O, or an F in a different molecule. Absolutely, answer D is the correct response. Okay, so let's look at these three molecules here. Okay, if they were to say, here's three different molecules, put them in order from, let's go, lowest boiling point to highest boiling point. Okay, so the lowest boiling point is the one that has the weakest, so weakest, and we're going to talk about this a little bit more in the next video, weakest IMFs, or sorry, I have that backwards, sorry. I'm going to switch those here. The lowest boiling point is the one with the weakest IMFs, and then the high boiling point is the one with the strongest intermolecular forces. Okay, so let's go through each of these and identify all of the intermolecular forces in all of them. So in H2, what are the intermolecular forces in that one? I just said it. Those are just London dispersion forces. And why? Because H2 is nonpolar. Okay, it has a nonpolar bond. It's a nonpolar molecule. Okay, where HCl has London dispersion forces, but also has dipole forces. Okay, and then HF, again, because it's a molecule, also has LDFs. HF is certainly polar, so it has dipole intermolecular forces, but then that H is bonded to an F, and it can form attractions with other fluorines in a different HF molecule, so therefore HF also has hydrogen bonding. So in terms of, in order from lowest boiling point to highest boiling point, the one with the lowest boiling point absolutely would be H2, okay? And then we would, after that, we would go HCl, and after that, we would go HF. So HF would have the highest boiling point, and H2 would have the lowest boiling point. Okay, now, hydrogen bonding, again, they really like intermolecular forces type questions on the test. So far, we've only talked about boiling points, okay? There are other things that affect intermolecular forces as well that we'll talk about in the next video, other than just the boiling point. But the boiling point is kind of the very most common one that they go to. If they're just asking a typical average intermolecular forces question, a lot of times they just talk about boiling point. But there are some other things that we need to be familiar with as well. And again, just know that, again, LDFs, London dispersion forces, are typically the weakest. Dipole are in the middle, and then hydrogen bonding, absolutely without a doubt, is the strongest of those three. And you'll find a lot of multiple choice questions that that the answer ends up being something dealing with hydrogen bonding. A lot of your questions in your homework packet for these three videos deal with hydrogen bonding.